Today we'll be going over some probability theory. So what we have here is example 1. Suppose S is equal to 1, 2, 3, 4, 5, and 6. We have three events defined as following. A, B, and C, whereas A is equal to even numbers in S, B is odd numbers in S, and C is 3 and 4. So we know that for A, it is even numbers. So the even numbers are 2, 4, and 6. So we know that. And then for B, odd numbers. That is 1. Oops. Sorry about that. 1, 3, and 5. And then C is just 3 and 4. So it says find the following: A union B, or A or B. So that is what's the elements in A or the elements in B, which is 1, 2, 3, 4, 5, and 6, because both A and B consist of those numbers, or you could say this is equal to S, because right here. So then we have B. B is A intersection B, or what's in A and B. So if we look back, we have for A it's even numbers, and for B it is odd numbers. And we can say that this is the empty set because there are no elements in each. So now let's do C. A intersection C. A intersection C is A and C. So what's in A and C? Well, all we can see is for A, there's a 4, and for C, there's a 4, so that's the only one. So our only outcome is 4. Next, we have D, which is B complement. B complement is basically anything that's not in B. So if we look here, B consists of odd numbers. So B complement is even numbers. So that is 2, 4, and 6. Or you could say this is just equal to A. Yep. Now for E, this one's a little bit tricky, but it says A union B complement. So first let's take it step by step. A union B, that is back at problem A right over here. So A union B is basically just S, but S complement intersection C. So we know S is 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5, 6. But S complement is basically not those numbers. So this is basically the empty set, because S complement is the empty set, and anything in the empty set intersection C is basically just the empty set, nothing. And finally we have F right here, which is A intersection B union C. So let's take it step by step. So A is, we all know, is even numbers, so 2, 4, and 6. And then we could write the intersection. So now what's B or C? So everything in B or C. So we have 1, 3, 5 for B. You can write 1, 3, and 5, and then everything in C. We already written down 3, so all we gotta write down is 4. And there you go. That's how you do this, the introduction. Hello everyone. So today we'll be going over this example right here, example 2. It says show that A intersection A intersection C complement is equal to A intersection C complement. So for this, we have to just show that they're both equal to each other. So what we could do is we can start with the left-hand side using De Morgan's law. So De Morgan's law is basically A union B complement is equal to A complement intersection B complement. We basically have to distribute the complement and change the union to intersection, or A intersection B. So if you're started with intersection complement, we could just do it vice versa. So A complement union B complement. So for the left-hand side, we get A, let's write equal A intersection, we just leave that alone. Then we get A complement union, since it's intersection, we gotta change it to union, and then C complement. Then after that, we gotta do distributive property to both values, and then we get A intersection A complement union A intersection C complement. So right over here, we know that this is the empty set because you can't have something in A and not in A. So this is the empty set, or phi union A intersection C complement. And then we could just get rid of this right there. And then we have A intersection C complement. And as you can see, that this is also equal to this. And that is how you do the proof. Thank you, everyone.